Oh, hey guys, welcome to Loving the Physics with Mr. Goldthorpe. Today we have a pretty short lesson to get things started. We're going to talk about wave interference. So before I do, I'm going to actually just show you a quick video applet. Here comes some technology. Okay, so I have this on video and kind of walk you through it. So if you guys want to, you could at any time go to this Surendranath site, General Physics Animations. I really encourage you guys to try it yourself. Let's get this started. Okay, so I'm just going to do a little voice overlay while I show you this video that I created earlier. You can see that I'm so good at this. Okay, so you just go over to Addition. And here we can actually create waves to interfere with each other. So I'm going to go with unequal amplitude waves that are pulses. I'm just going to show you what this looks like when they're in phase. So we call these two pulses positive pulses because they're above equilibrium and they're of unequal amplitudes. And we're just going to see what happens when we bring them together. Cool. So notice that waves, they have a beautiful property of just going right through each other and not being affected at the end. But what we need to do in this lesson is to be able to draw what you see right here, which is that resultant wave. And you notice that we have two positive pulses coming together, and notice it makes an even bigger, higher amplitude pulse. That will be called constructive interference. So now we're going to move to out of phase. So one's going to be a positive pulse, the red, one's going to be negative, which is the blue. So let's see what happens when these things come together. Cool. So again, they go right through each other and not being affected afterwards. But let's take a look at them when they're together. And we call this superposing. When they superpose, they make a brand new wave, the golden wave. And one being positive, the other one negative, if we add them together, we get the golden wave. We'll talk about how to construct that later. This is called destructive interference because they make a smaller amplitude wave. Now this time we're going to have equal but opposite pulses coming in. I'm going to focus your attention on the middle there where the pointer is showing. Just take a look at that special location. Whoa. So just I'll point right to it, right at that one location. Notice that that one, it never moves. And what happens here is you're getting perfect destructive interference. They are equal but opposite at all times. All right, so this is the area of interference. So our job now is to be able to actually sketch those diagrams. So let's go back to our lesson here. Okay, did that. So if you want to take notes as we go along, you're absolutely welcome to. Just pause if I'm going too quickly at any moment. I mean, feel the power, you guys. You get to pause me whenever you want. You just can't delete me in reality. Okay, so let's do a little comparison. Turns out what's really important in physics is the difference between particles and waves. Really important for Physics 30. On the left-hand side, when you have systems of particles, for example, cars, when they're coming together head-on, they actually collide. And hopefully this has never happened to you, nor will I hope it will ever happen to you. But two cars will collide. They will not go through each other. That would be bizarre. They slam into each other. As opposed to waves, as we saw on that video, when waves actually come towards each other head-on, they don't slam into each other, they superpose and create a different kind of a wave. So they superpose and they make a new kind of wave, as we can kind of see right in the middle here. So it's superposing to make a new wave, but then at the end, as you can see right here, they leave unaffected. That's typical for wave behavior. So this is a really good way of comparing particles versus waves. Really important when we get to Physics 30. Okay, so we're going to focus our attention though on the right-hand side over here, this idea of wave interference or superposition. Now, as I mentioned to you guys, there's a couple of different kinds of interference that we want to talk about. Oh, and you know what? I don't think I even need this. Yeah, sorry, I'm going to move over to my notes. There we go. Okay, so as I showed you, let's move on now to this idea of the principle of superposition. Sorry, you'd think I'd be much more ready. Okay. All right. Anyways, rookie. All right. So as you guys can see in the notes here, and again, pause if you want to take these notes. So whenever we have waves occupying the same position, so let me just kind of change the color here so I can highlight this. If they occupy the same position, we call that superposing. And when they do, they interfere and make a brand new wave. And we call this new wave a resultant wave. And that's what we have to be able to draw. Now the principle of superposition, as we see over here, and I guess I'll just change the color, just having fun with colors today. What we call the principle of superposition is actually a very simple idea. It tells you that the resultant is simply going to be the sum of the displacements. So all we have to do is add up the displacements and we get the resultant displacement. But keeping in mind that if you have a positive pulse, you have to use positive numbers, and negative pulse is negative numbers. So here's a simple example on the bottom here. And if you want to just pause for a moment, you can try answering this question yourself. All right, let's give this a try. So we're looking for the overall displacement, and we're given two different displacements from two different waves. So, and remember, the principle is just simply add them together. So in this case here, we're looking for the overall displacements. We'll just call that delta D total. But we know that that just has to be the sum of the two displacements. So delta D from wave 1 plus the delta D from wave 2. It really is that simple. But notice that wave 1 is 3 centimeters above equilibrium. So that's going to be, logically, positive. Ooh, what happened there? Okay, let's get rid of that. That'll be positive 3.0 centimeters. So that's our first displacement. And our second one has a displacement of 9 centimeters below. So, as you might suspect, it's going to be negative 9 centimeters. And we just add those together. So logically that just becomes negative 6 centimeters, or simply 6 centimeters below equilibrium. So you can see this is not a very difficult concept. Mathematically, it's very simple. You simply add the two together. Good. Okay, so that's the principle of superposition. Now, let's talk about the types. This is what I was looking for before. So again, if you want to take some time to write these notes down, just pause whenever you need to. The first thing I want to talk about is this thing called constructive interference. Now, if it's constructive, they actually add up to a higher amplitude wave. And there's two situations where we can have that. The first one is when you have a crest plus crest, if you add two crests together. So A would represent one crest and B would be another crest. And what happens when they come together is you add the two together and you get a much higher amplitude. So the key idea is this is going to be a higher amplitude wave, or a higher energy wave. If that happens, that's constructive interference. But what's interesting is that's also true for a trough and a trough. These are two negatives, and the two negatives add up to make an even bigger negative. That is still constructive interference. So those are the two cases for constructive. Now, destructive. So destructive interference happens when they come together to form an even smaller amplitude wave. And you guys can see here that these ones that I've shown you with A and B, they are equal but opposite. And when they're equal but opposite, you can see that when they add together down here at the bottom, they completely destroy each other. We call that total destructive interference. Now, believe it or not, we're saying that two waves can come together and form no wave at all. So this would be like two sound waves coming together and destroying each other and having no sound, otherwise known as silence. Now, how is it possible for two sound waves to come together to form silence? So just to briefly reveal an application of that, this is what I wanted to get to here. So I'm just going to get to this point right here. There we go. There we go. Now, I'm sure you guys have heard about noise canceling headphones. So this is kind of a relatively new technology where we can kind of remove ambient sound. And the logic is, so I'm just going to walk you through this one. So we start out with the ambient noise. So this ambient noise could be, let's give you some examples. Maybe you're on an airplane and you have that background hum. Or you might be on the road in a car and you've got the road noise, the hum that you get from that road. Or you might be out mowing the lawn and you get that constant lawnmower sound coming in. And those things can be pretty loud. And typically, if you want to hear anything, you have to put, like if you have headphones on, you need to put your headphones on even louder to go overcome that external noise. But you got to realize that by doing that, you're going to do damage to your ears. So is there any way that we could remove that external noise? Well, it turns out you can using the idea of destructive interference. So what happens is your headphones actually have a power supply built in. So they have their own batteries and they actually produce sound. What they do is they actually take the sound that's coming in, the one I'm showing you right here, they record it and then they invert it. And when they invert it, it goes what we call out of phase. So these two, when you take a look at this one, here's the inverted one. We would say these things are out of phase. And so when you bring them together, so essentially the noise comes from the outside, the sound waves are also produced by the speaker, and both of them go into your ear. But they go in completely out of phase. So we call this out of phase. And if you notice at every given location here, they are equal but opposite waves. And if they're equal but opposite, they cancel each other out and you get absolute silence. We've actually removed the ambient noise. So therefore, you can actually put on your own music, whatever it might be, and put it at a much smaller volume and protect your hearing. So this is the idea of noise canceling headphones. Pretty cool concept. Okay, we're almost finished. All we have to do now is this. And this looks pretty intimidating, but this is basically going to bring all this stuff together. We're going to have to learn how to sketch a resultant wave. So what we're actually seeing right here are two different waves that are superposing. So we actually have, for example, let's say we call the solid wave, let's say we call that wave 1. And let's imagine that wave 1 is moving to the right. At the very same time, now let's use a different color for this, we have the dotted wave, and let's say we call that wave 2, and let's say that one happens to be moving to the left, for example. But what we've done is we've paused it at one moment in time. So one wave, the dotted wave, is on top of the other wave. So they are occupying the same position. They are superposing. And the question is, what would we see at this moment in time? So we're going to learn how to draw the resultant wave using this principle of superposition. So if you want to, you're welcome to trace this. You just put a piece of paper over top of this and then trace it out, or you can roughly sketch it, whatever you guys want. I think I have a copy of this inside your workbook as well, so you can do this inside your workbook if you'd like. All right, so we're going to give this a shot. I'm just going to change it to a appropriate color here. Actually, you know what? I'm going to go with, let's go back to purple here. Okay, so first of all, we want to identify what we call the bounds of superposition when they're both going to be adding together. Now, if you guys notice, if you start from the left, we're going to start over here from the left-hand side. And you'll notice at the very beginning that we have absolutely no wave. And I'm just going to draw over top of it with purple. We have no wave whatsoever up to there. But then we have only one wave. So I'm going to draw over top of that. And now we have only one. All the way up to this particular point right here, there's only one wave, just a solid wave. But you'll notice at this moment, now we have two. So I'll just use different colors, go with red. If I kind of make it visual, at this vertical dotted line, that's where the interference will begin. So now we have two waves. Here's the question for you guys. Can you tell me where the interference will end? And hopefully you're seeing that it's where the dotted wave ends. So at this location, that's where you have the end of interference. And if I go back to purple here, I can now finish off the outside wave. Outside of that, oh, that was really well done. If you drink enough, that was pretty well done. There we go. Okay, so there's the waves outside the interference zone. Good. Now let's try talking about the area of interference. Now I want to just, you'll notice that we have grid lines here. So I'm going to show you one particular grid line. Let's focus our attention, let's go in blue, on this one right here. So I'm going to focus on that grid line. And I want to figure out where the resultant displacement will be for this particular particle. Now, the first thing we want to do is we want to figure out what the displacements are for each individual wave. So if we focus our attention, let's say, on the dotted one, you'll notice this one here, you always start from equilibrium. This will be 1, 2, 3 above equilibrium. So we could call its displacement positive 3. Now we could do the same thing for the one below it. That's going below 1, 2, 3, 4, going to that part. And see, you see that's like 4.8 below. So we call that negative 4.8 down here at the bottom. So now we have the two individual displacements, and like we did on that example, all we do is simply add these two displacements together. 3 plus negative 4.8 gives you negative 1.8. So from equilibrium, we go down 1.8. Takes us to about here, give or take. It's a very approximate thing. And that would be the resultant position of that particular particle. So I kid you not, that you just have to do this same procedure for every single grid line all the way from left to right. So why don't you take the next few minutes and just try to finish up all the other dots, every other grid line location, where would the resultant dot be? Okay, well, I'm going to show you approximately where these dots happen to be. So, and I'm just going to do it approximately. I'm sure you guys will have added up all the different displacements. I'm just going to do it approximately. And here's a kind of a rough way of actually doing it. You'll see that for the first, if I'm looking at the first one, you'll notice that the dotted one is basically 2.2 above. And what you can do is you can actually start from this one down here, from the other one, and go 2.2 above that. So you just go 1, 2.2, and that takes you about to here. However you guys want to show your work. Anyways, I'm just going to show you approximate locations for each of them. And again, yours can be different than mine a little bit, because this is a very rough approximation. This is really fun. Give or take. Okay, so yours will be approximately like that. I'm sure yours do a much better job than mine. Okay, I wanted to talk about the last three, because the last three are a little bit more interesting. So if we start on the next, so I'm going to focus now on this particular grid line. If you'll notice, and by the way, let me just change the colors of all those and make sure they're all purple, 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 etc. I gotta stay consistent with my colors. Okay, now for this one over here, you'll notice that the solid one essentially has an amplitude of 0, or a displacement of 0. Whereas the other one has a displacement of 3.5-ish. Well, essentially we have 0 plus 3.5. And I hope you understand that's going to be 3.5. So that takes it right on. That'll put it right on the dotted one. Okay, so that's an important location. All right, so far, if we're going to kind of summarize this location, all the way along here, for the first part here, you'll notice that we have one wave being positive, the other one being negative. What kind of interference is that? So this part here represents destructive interference. So that's destructive. One positive, one negative to make a smaller amplitude. Good. Now let's move on to the last couple. So now I'm going to focus my attention on this one. Let me get rid of all the other stars so there's no confusion. And what you'll notice is that the solid one has an amplitude of about there, or displacement about that. That's about what, 1.8? So 1.8 positive. And the other one has a displacement of about 3. Again, we simply add those two together. So 3 plus 1.8 gives you 4.8, taking you up to about there. So I'll do that in a different color. That's about 4.8. And let me just kind of get rid of those markings now. And let's try the last one. And this one is the most challenging. You'll notice how they intersect at this location. So if I put a dot here, you'll see that that looks like it has a displacement about 2.2. So it's about 2.2. But notice it's also the displacement of the dotted one. So there's another 2.2 because there's two of them, the dotted and the solid. We have to add those two together. So we get 4.4. So again, I'll change the color. So you have 1, 2, 3, 4.4. Takes you about right there. I'll erase those. And this. Good. Now, if I kind of highlight those locations, so from here to here, you'll realize in this case we have two positive pulses. And that'll represent constructive interference. Now, all you have to do to finish this up is just to connect the dots, just like you did in elementary school. And I can fill that in a little bit so it's a bit clearer. And there you go. As long as you have a diagram that's approximately looking like that, you would get full marks. So that's the idea of doing interference. All right, like I said, a pretty short lesson today. Hope you were able to love at least a little bit of physics, and I'm looking forward to teaching you guys next time. Have a great day.